Also, this one took me like, well, we're going over that one too, because I don't understand what's going on.
If the acceleration is 0,
Okay.
the whole purpose of figuring out what the direction of acceleration is to establish your coordinate system.
Okay.
If acceleration is 0, you've got a lot more freedom to choose your coordinate system.
Right.
So you choose it that was going to require the least amount of decomposition.
Acceleration roll is what I'm saying.
So you're going to make I hat or J hat down.
Yeah, J
Okay.
hat is down.
So it's not the acceleration that's down, it's your coordinate system.
Yeah.
Okay.
Yeah.
So now equations of movement.
So for I hat, it would be other force, which is F, minus Y equals 0.
Yep.
And then J hat would be weight minus friction equals mass times acceleration.
Okay, what's the acceleration?
0.
Yes.
So it's 0.
Yes.
Sorry, completely forgot about that. And then that means that force equals, or the other equals normal force,
Yes.
and weight equals friction.
Yes.
And obviously they help me with this because
Substitution is next.
substitution is next. Because weight equals mg equals friction, and friction is mu s times y.
Yep.
And we know y equals the other force.
Yep. So you know mu s, you know m, you know g.
Do I know the mass? Yeah, I know it's, so it would be 20, wait, one second. So the mg equals mu s other force, which is equal to 24, which is the mass, times 9.8, which is the g, equals 0.7 times other force. 24 times 9.8 is, what do you think that is off the box?
24 times 9.8?
Yeah. A.
This means something a little bit under 240.
Yeah, you're right, it's 235.2. 235.2, I just have to test it. 0.7 divided by 0.7. The other force is 336 newtons.
So what was messing you up was,
It was, I just don't think I'm smart enough to answer the question. That was what was messing me up.
I'd never ask a question that I don't think students can handle,
Yeah, I
despite what some students have claimed in the past.
Okay, that's been about one thing.
I have asked questions that I thought would be a little bit challenging for students.
I don't even know how to start this.
Any other questions?
Yeah,
Okay.
can we go over all of question 7? Don't know where to begin. I thought I did.
Yes.
Exactly.
Okay.
Everyone is
So
gonna
So
be
what would you suspect, what would you expect is the first step?
Okay, I know what the first step is.
What's
I
that?
do know
Gibbons.
what it is. It's
Okay, so
the force diagrams.
That's
1, 2,
either that or draw the picture.
Mass is
Okay,
1, 2,
mass.
3, 4. Look, I really tried so hard.
Never mind. Nah, you're good, you're good. What did you know?
Oh, you have that?
I literally got it from Stephanie too. I was just like wondering if I could reserve this card now.
Whoa.
No, that's
Okay, I did it. I did it? I don't know if I did all of these, and I'm
that the right labeling?
That's a lot of.
Is that a right or wrong?
Okay. Mass 4 hanging out on the left-hand side, Mass 2 dangling
Yeah.
down,
That's correct.
Yeah.
and this is being held up mysteriously.
Yeah, it's actually like, I guess it doesn't.
Oh, I did it overhang.
It doesn't. I'm sure it's the same.
It's not supposed to.
Is that blue line another object, or?
That is my attempt to give some justification for how this roof is being held up. Yeah,
So,
it's
in
part
the
of this.
problem, it's non-existent.
In the problem, I forget the way I actually drew it. I did
This master set 6.
overhang,
4 and 5.
4 or 5 application.
Okay, wait.
Yeah.
If we were to do this as a 4-step. The first one and 2 years on.
Something like that.
Is like.
All right. Oh, and Gibbons. Mass 4 was Mass 4.
2 kilograms.
All right. Mass 2.
Minus 2 is 2.5 kilograms.
All right. Mass 1.
6 kilograms.
6.
Yeah,
Mass 3.
5 kilograms.
All right. And we have a coefficient of friction here, I believe. Use of S equals
0.8.
equals what?
0.8.
0.8. And did I give you use of K?
Yeah, 0.3.
Any other givens?
No.
Okay, we got the givens down, we got the problem drawn. What's the first step?
Force diagrams.
Yeah. So I'm doing a force diagram of what?
Huh?
I'm doing a force diagram of what?
The mass is in the rope.
Sorry?
The mass is in the rope.
Okay.
The rope that is holding, the rope that is connecting to the rope holding M4.
It's a
also
rope
kind of-
connect, M4 is being held up by a rope that's connected to M3.
Yeah, what's that rope called? Cause I can't.
Oh, I wrote R4 for rope
It's
4.
an R? Okay.
Yes. Yeah, the marker was fading.
Stupid.
So I've got. That's M4, M3, M1. I'm gonna give myself more room than that. Rope 1. Rope 3. Rope 2. Mass 2. And then I have a connection point right there. Okay. I've done the first step of the force diagram. Now what?
Now we do our F-tom.
Okay.
So, we can start off with friction, because that's the hardest one, and I need to learn. So with
Sure.
the friction, that mass 3 exerts on mass 1 would be to the left. I made it
You
up.
mean to the right?
To the right. No, to the left.
Okay. So M3 is exerting a friction force this way on M1? Is that
Wait,
what you're
that's
saying?
where the arrow would be?
Well, you just said that that was the force on M1. So I would draw my arrow on M1.
Wait, was that?
That's why sometimes you get picky about prepositions. It tells me exactly where the arrow to draw. If I can state the force correctly, it tells me exactly where to draw the arrow.
No, I changed my mind the other way.
So M3 is trying to send mass 1 to the right.
No. Keep it this way. So, I don't know, yeah. That's what I'm feeling.
Stephanie, did you have a different opinion?
Because I don't really know how to explain it, but I kind of imagine it like how you should like stepping, like when you walk, like everybody's trying to go that way, pushing Mac one the other way.
If M3 is trying to go that way, which way would friction act on it?
This other way.
Friction would act that way on mass 3.
I'm always gonna trust you.
So-
It was the one with the car and everything.
Okay, and then we can do the table in mass 1,
I was asleep.
Okay.
or is it a friction arrow? So, mass 1 wants to move that way, right?
Yes.
So, that means that the friction mass 1 exerts on the table. 1 second.
Do you want to come up here and draw the arrow, because you're struggling with the language?
No, I'm struggling with friction. I don't know why I'm not. Oh, no, it's this way. It's this way. The arrow's this way. Connor, but you just said on the table, so. What, can you draw it the table really fast? This is the only part that's confusing me, by the way. So the arrow is this way.
This way on the table?
Yes.
And so that way on the mass?
Yeah. That is what I mean.
That is what you meant?
That is what I meant, yeah.
Okay, because that is what you said, that was
Yeah,
true.
yeah.
Okay.
Yeah. Is that right?
Yes.
Oh, okay.
Because as you said, mass 1 wants to go that way. Friction says, no, not in my house. I'm gonna try to hold you back.
I'm so sorry, guys. I'm just not confident in myself.
I know there was some.
You said mass 1 wants to go this way?
Wait, sorry, Stephanie?
I know there was some sort of situation you said where the way that the object is moving or wants to move and the friction.
Are in the same direction. That's when you have, I guess, some internal device trying to move the body part that's touching it, or trying to move the part that's touching it in a certain direction.
So almost like an outside force.
Not, I would not say that, I definitely would not. But when I walk, I'm pushing my foot backwards. So even though I'm moving forwards, it's the foot which matters in that case. Or in the case of a car, it's not which way the car is gonna go, it's which way the tire wants to move.
And I believe that's all for friction. So,
Okay.
anyone else can like speak on what they want to do.
Personally, I'd recommend doing friction last. I know you stated the reason why you wanted to do friction first. And the reason why I suggest that is I think it's a little bit clearer about which way friction has to act. If you get all the other forces correct, that there are certain situations where it's very clear which way it has to act if it's in static equilibrium. But each to his own taste.
Yeah, gravity. I mean, yeah, the
All right, so wait, we did friction. All right, so gravitational force?
Down on everything.
Yeah, that pretty much sums it. Let's see. We have the weight of 4, the weight of 3, the weight of 1, the weight of 2, and then the ground. If we're doing the full force diagram, there'd be an upward force on the ground. All the ropes are ideal, so they don't have weight. If you do want to throw in the weight of the ropes, then have fun with the rest as well.
No, we don't want to do that. So we're done with gravity?
Yeah, I guess we're done.
We can move on to normal force.
Okay.
So the only two things touching each other
to,
Okay then.
well, we have to include the fact, since the table is touching M1, there is a normal force there.
I lied. Okay. I just meant like, we don't have to draw the second pair, do we? If we don't.
Oh, we don't have to draw the force on the table, no.
Okay, that's what I meant. Okay, so, for M3, the arrow's up. And then M1, arrow down and arrow up.
I hope you would be more specific when you actually solve the problem.
Yeah, I was really. I think that's it.
Yeah, those are the only ones that matter. There is a normal force acting over here, but ultimately, that one doesn't matter.
For this ideal.
Yeah. I mean, even if you looked at the forces acting on the rope, since we assume it's massless, you have sum of forces is equal to 0.
That Y1, is that acting on the ground or the box?
That's with the table. It's, the Y1 is the normal force between the mass 1 and the table.
Why'd you write the arrow down if weight
On the
is?
table, or this one.
Yeah,
That's, because that's the normal force between mass 3 and mass 1. Mass
the
1's
one
touching
right
2 objects.
underneath Y3, that one.
That's Y1,
Then why'd you write Y1 there?
because that's the table. Forces come in pairs.
Yes, I know.
I didn't have to write this one. But I thought there was some confusion at some point over,
Can you erase that and let me reinterpret it in my mind?
you recall that?
Okay, that works. So Y1 is acting on the box so that it doesn't phase through the table.
So it doesn't what?
Phase through
Oh, yes,
atomic
yes,
stuff.
I missed the verb. Got it.
Okay. So it is working on the box, so it doesn't phase through the table.
Correct. That's it for the normal forces that matter.
Okay, tension.
Yes.
I guess I'll start this off. There's tension for mass 4 and the rope. Now they're pointing at each other.
So pointing at each other. Okay, so I've got, call it T4 and T4.
Yeah. And then mass 3 and the other part, the end of the rope.
FT3, FT3.
And then there is the rope connecting to mass 4.
FT1, FT1. I am gonna make one change here. This is the same tension in both spots. It's an ideal rope, so, and I'm also gonna use 3 over there. So, I'm just gonna call that FT4 at both ends. All right, and
And there's tension on M2 at the end of rope 2.
FT2, FT2.
And then there is friction, tension, sorry.
One of those words.
Yeah.
Oh, by the way, and I don't know if it was in this group or the other group, but somebody made reference to tension force. Tension is a force, it's redundant to say tension force. All you have to do is just use the word tension. And I can't remember if it was someone in here or
It
someone
was
in the other
not
class.
someone in here.
Was it?
Because I would have remembered it.
Oh, so it wasn't you.
Yes, that's exactly right. There is.
All right. So we're missing a couple more pairs.
There's tension between the ropes, right? 'Cause they're
Yeah.
attached.
Yeah, didn't they actually state there's the force diagram of the masses and the connection point?
Aren't those ideal?
The ropes aren't ideal, but there's still something holding them together.
Oh.
Did I comment on?
No.
There, hint, start with the force diagram from S's 1, 2, 3, 4, and the intersection point of ropes 1, 2, and 3. Did I say intersection point or points?
Intersection point.
Point, yeah, same one. That's the intersection point of 1, 2, and 3.
That's not one.
So, I got FT2 here, FT2 here, FT1 here, FT1 here, FT3, FT3, and if we want to throw the wall into it, FT3, FT3.
Why, are they different tensions coming into this, like, intersection?
So how are the ropes attached to each other?
I don't,
Do you accept that it can't be one rope?
right,
Okay, so if it's not one rope, then we have, sorry, wondering if that would make an interesting problem.
Don't, please.
So there's some connection point right there. So it's different tensions acting into it, so picture it's a ring or something like that, that the ropes are attached to.
okay, so, because. Okay,
Or
I don't
They
wanna
could-
explain it, cause I feel like you're gonna say that I'm explaining it wrong, but. Is it because like on one end of, like for example, on rope 2, you have FT2, which is the tension between rope 2 and mast 2, and that has to be the same on the bottom as on the top of the rope, so therefore that tension is not gonna be the same as, for example, rope 1, which has a different, FT1
Yes.
force when attached to that one mast.
Yes. All right. Tension done. There's no other. How many equations of motion will there be?